Chapter 6 Synchronization Tools. Background. Cooperating processes can either affect or be affected by each other, can share a logical address space or be allowed to share data. However, concurrent access to share data may result in data inconsistency. Hence, we need to ensure the orderly execution of cooperating processes that share a local address space to maintain data consistency. The integrity of data shared by several processes or threads. Concurrent execution. A process may be interrupted and at any point in its instruction stream. The processing call may be assigned to another process. Parallel execution. Two or more instruction streams representing different processes execute simultaneously on separate processing cores. Consider an example of how this is happening. Let's revisit the producer-consumer problem, where two processes share data and are running asynchronously to count items in the buffer and an integer variable count initialized to 0 increment every time we add a new item to the buffer, decrement every time we remove one item from the buffer. Data inconsistency. Although two processes are current separately, they may not function correctly when executed concurrently. Suppose that the value of count is currently 5. The producer and consumer concurrently execute two statements count plus and count log. Then the value of the variable count may be 5, 4, 5, or 6. Is it possible? Why? How these results can happen. Note that two statements count and count may be implemented in machine language as follows. Register 1 count register 1 equal register 1 plus 1 count register 1. Even two register 1 and register 2 may be the same physical register. The contents of this register will be saved and restored by the interrupt handler or shader. Let's condition a situation where several processes or threads access and manipulate the same or share data concurrently, and the outcome of the execution depends on the particular order in which the access takes place. To guard against the race condition, we need to ensure that only one process at a time can manipulate the shared data. To make such a guarantee, we require that the processes are synchronized in some way. To say process or thread synchronization. The critical section problem. Consider a system consisting of n processes. Each process has a system of code called a critical section, in which the process may be executed and updating data, in which that is shared with at least one other process. The important feature of the system is that when one process is executed in its critical section, no other process is allowed to execute it in its critical section. The critical section problem: no two processes are executing in their critical sections at the same time. To design a protocol that the processes can use to synchronize their activity so as to cooperatively share data. Section of code to enter section. The section of code to request permission to enter its critical section. The critical section follows the entire section. The exit section follows the critical section. The remainder section is the section of remaining code. The requirement for the solution: modal execution. If process Pi is executing in its critical section, then no other processes can be executing in their critical section. Progress avoid deadlock. If no process no executing it in its critical section and some processes wish to enter their critical section, when the selection of next process when enter its critical section next cannot be postponed indefinitely. Brown waiting, avoid starvation. Above or limit or the number of times that other processes are allowed to enter their critical section. Example of latch condition. A simple solution in a single core environment prevents interrupt from occurring while a shared variable was being modified. We could be sure that the current sequence of instructions would be allowed to execute in order without preemption. No other instruction would be run, so no unexpected modification could be made to the shared data. Unfortunately, not feasible in a multi-processor environment. Two general approaches: preemptive kernel and non-preemptive kernels. Non-preemptive kernel, a kernel mode process will run until it exits kernel mode block or voluntarily, yet the CPU is essentially free from latch condition on kernel data structures. Preemptive kernel allows a process to be preempted when it is running in kernel mode. Essentially difficult to design, but feasible since it may be more responsive.